Okay, welcome back. Now what we want to look at is electrical machines, motors. And you will find this is at level 3, okay? So for you guys doing level 3, you should find this quite useful. Now, if you're at level 2, this will prove to be useful to you as well in preparation for level 3, okay? Now, this will be sitting girls level 3. Let me just go back a little bit, make sure that we have it in place and that it is seeable, okay? And that it's in frame. Okay. Now, what I want to look at is the contents. Now, you need to read the information for yourselves. You need to do additional research. And always apply safety, safety, safety. Okay. Now, here we have what we call synchronous motors. Three-phase AC motors. Single-phase AC motors. AC motor starters and speed control. DC motors. DC motor starting and speed control. Motor enclosures and maintenance. Okay. I'm just going to do up that for you so you can make sure you can get that in fully. Okay. I'll pan that out a little bit more. Okay. Right. Okay. Now, three-phase AC motors, synchronous. Now, this has 3 windings connected to a three-phase AC supply, which form a rotating magnetic field in the stator. Okay. Now, the stator is the outer shell of your motor. Okay, and that is the fixed element of the motor within that field. Okay. Now, this magnetic field travels at synchronous speed n. Its speed is determined by the frequency of the AC supply and the number of pole pairs of windings. Okay, that's pairs per poles. Okay, so if I have 4 poles, how many pairs do I have? That would be 2 pairs. If I have 6 poles, how many pairs do I have? That will be 3 pairs of poles. Okay. This type of motor runs at constant speed. Okay. Now, what I need you to do here is 1, do a little bit of research for yourself to find out what the word synchronous means. If you type this into Google, it will give you a lot of information. Make sure you understand what synchronous and non-synchronous means, okay? That is your grounding for yourselves, for your own research. You add that to the information I'm now giving you as well, okay? It makes more sense when you actually do a bit of groundwork for yourself and you can see what the instruction is trying to say, okay? Because then it allows you to interpret your brain to interpret what you see in your own mannerism. Okay. Synchronous motors. Okay. Original synchronous motors had copper coils in the rotor and the stator. So the original ones had copper coils in the rotor and the stator. Okay. But as time went on, we developed another mechanism which allows us to do more work efficiently using a different system. Okay. Sorry about this if this keeps shaking all the time. It's just that my table is not even. Okay. So the stator has a 3-phase AC supply and the rotor has a DC supply. The DC supply was delivered via slip rings and carbon brushes. Okay. A synchronous motor is non-self-starting. Now it cannot self-start, it has to be started by some other means. It needed its rotor to be rotated to synchronous speed by an external motivator, i.e. another motor, before it would run. Okay? Let's move into this so you can see this for yourselves. Okay. Pan back out a little bit. Okay. And again, do some research for information on synchronous motors. These motors can only run at synchronous speed or they would stall. This complicated system was overcome by the development of the induction motor. Now do a bit of research in regards to induction motors. See how they are used, where they are used from, and how they are applied. And mainly look at how they are constructed, okay, as well. Now here's your diagram of your synchronous motor. You have your slip rings, you have your external DC supply which feeds your coil, and this is your rotor bar, okay? And that rotor bar will be rotating within the stator field, okay? Let me just go down a little bit to bring this in so you can see this in more detail, okay? Okay. Make sure we can see this before. Okay, right. Now remember, you can draw these diagrams out, okay? That's why I've taken the time to linger, because you can pause your video and make it, bring it into play. Okay, let's just go back a little bit. Bring it back into full view, okay? Okay, thank you, that's good. Now use the information, use the knowledge given, apply it. It's not going to jump out on the screen and into your head. You have to sit back and read it and take the time to read it. Treat it like a football match. 2 hours running. Okay, 90 minutes. Now induction motor cage rotor. Now let's look at this. Okay, let's bring this into view as well for you. Okay, you can see this for yourselves in full. Okay, and that's what it looks like in theory, in practice. Okay. And you will find that I've given you some of this already in the playlist in regards to electrical principles and motors. Okay. Okay, let's turn back a bit. Okay. Let's see that in full. Okay. Okay, right, good. Now, I brought this in from the bottom okay, which I should have bring in from the top and read. But you will read this for yourself anyway. Okay, so it doesn't matter whether I read from the bottom up or from the top down. You will still need to read it for yourselves. So the rotating magnetic field in the stator induces current magnetism in the cage rotor, which in turn is attracted to the stator. As the magnetic field in the stator is rotating, the attraction between them causes the rotor to move. Okay, let me select each section for yourself so you can see that you need to be able to read it for your own. Okay. Right. Okay. Look up. Okay, thank you. Okay, bringing it to play. Let's just make sure we get it on screen in full view. Right, next. Cage rotor motors are quite efficient and do not require brushes or slip rings. You can see that from here. That's your rotor, which is being attracted by the magnetic field set up in the stator, and that causes that to rotate at a massive rotation, and it has quite a good torque on it as well. Now, this swivel cage was constructed from aluminium with shorting rings at each end and clad in laminated silicone steel. The laminations are skewed to aid starting and quieter running. Now when it says skewed, it means that these here are set off at a slight angle. Okay, they're not going straight across, they are deliberately set at an angle to give that quieter running and more efficient starting. Okay. Okay. Okay, induction motors replaced the copper windings in the rotor with a cage design called a swivel cage. Okay. Now, you cannot read this information in 5 minutes or 3 minutes. It takes days to prepare this kind of work. Days. Well, sorry, I apologize. It may take 28 to 30 days to do this work. So it can come to you. And it appears that it's been done in 10 minutes. That is not the case. It takes weeks for this work to be done. So the least you can do is at least spend a couple of hours reading through the work and seeing the information for what it is. Okay, thank you. Let me just make sure I can get this at an angle that is correct. Okay. Okay, thank you. Make sure we're in frame, and I believe we are good. Okay. Now, induction motor wound rotor. Okay, you can see here the slip rings, okay, and that is your rotor, okay. Now I've always admired the way that these things have been done, how they've been built, and how the wiring of each single cable. Remember that these windings here are made up of single cables, many single cable turns. It has always fascinated me. But then again, it's probably just my simple mind why I'm so amused at it. Sorry about that. Okay. So induction motor, wound rotor. Now, wound rotor design has the advantage of a far higher starting torque. Okay. Okay. This is achieved by adding external resistances to the rotor winding via 3 slip rings brushes. Okay. Now torque is thus controlled by changing the resistance of the rotor windings. Current and magnetic flux also change as the motor runs up to speed on the load. So what we are saying here is that this motor, we can start it under a massive load, but because we can control the speed at its starting torque, we can actually get it to start very slowly, and then slowly, and then it builds up and it builds up, and then it reaches maximum speed and becomes very efficient in its running purpose. Okay. This system does have the disadvantage of a more complex design with copper windings, brushes, slip rings, and external resistance starter. Okay. Let me just make sure we can get this into play for you. Okay. Make sure it can easy to be read. Okay. And both wound and cage induction motor rotors cannot run at synchronous speed, but slip behind it at between 2 to 5%. If excess load is applied, slip increases and the motor would stall. Okay, so if you make the torque too difficult, the motor would begin to stall under its own load, and that will begin to. Now be aware that if a motor is stalling on the load and you still have a supplied load to it and current going to the motor, you're likely to burn the motor out, so be aware of that. So there should be mechanisms in place to protect the motor from excess load or overload. Okay. Okay. Okay, we're in frame. We are in frame. Yep, fully in frame. Good. Okay. Good. Thank you. Single phase AC motors. Unlike three-phase motors, which are self-starting, single-phase motors are not. Okay. A single-phase supply produces a pulsating magnetic field, unlike the rotating magnetic field that a three-phase supply produces. Now you are responsible for reading this information yourselves, okay? You don't need me to actually read it out to you, but I'm just giving you an overview. Single-phase AC motors require an additional winding in the stator. This is called a start winding. The start winding will be electrically out of phase with the run winding up to around 40 degrees. This produces a two-phase rotating magnetic field and the motor can self-start. This is created by causing a lag in respect of the waveform that is rotating within the motor itself. Okay. Let's just say first, it calls it a phase shift. Okay. At about 80% of full speed, the start winding is disconnected from the circuit by a centrifugal switch. Now do your research, look up this work here in regards to centrifugal switches, see how they operate and how they are used. Okay. The motor now has inertia and continues to run. Okay. If the start winding were to remain permanently energized, it will soon burn out. Pardon me. Okay, let's make sure you have this in frame. Okay, now read the information, extract the information, make it your own. Do not think you can just read it from the screen. It's not going to work because you have got to do and present your work in regard to your assignments and so forth. Okay. Split phase AC motor. Now this is one diagram you will need to draw out as well. Make sure you draw it out so you know what type of motor you're dealing with. Okay. Start winding has a slightly higher impedance than the run winding. This difference in impedance gives approximately 40-degree phase difference between start and run windings. Okay, it causes a phase shift. The phase difference sets up a two-phase rotating magnetic field instead of a single pulse field. The motor can now self-start. When rotor reaches 80% of full speed, a centrifugal switch disconnects the start winding. This design has low start torque and runs at constant speed. Reminds me of the motors I've seen in some vacuum cleaners. Sorry about that. This motor cannot be speed controlled due to the centrifugal switch. Okay, so the centrifugal switch has the effect that you cannot control the motor simply because of that centrifugal switch. Okay, let's just make sure we get everything in place. Sorry about that. Okay. Yes, we have everything in play, in frame. Okay, good. Good. Okay, thank you. Oh, one more piece. To reverse direction, swap start or run winding connections. Okay, so let me just take it down a little bit. Pick up that last bit of information that I didn't give you. Okay. To reverse direction, swap start or run windings connections. Okay, you can see it there. Okay. Let's go back up. Split phase capacitor start AC motor. And there's your diagram. Always draw out your diagrams in regards of these cases, okay? Sorry about that. Just make sure we're in frame, okay? Okay. A capacitor in series with the start winding gives a better phase displacement of up to 90 degrees. So here again, we are looking at a phase shift, which gives us a lagging phase that gives us the impression that the cycle of the motor can now rotate because the waveform is not consistent. It is not one is constant to your 50 cycles, one is out of phase with your 50 cycles by 90 degrees. Okay, that's just a simplistic way of looking at it. Now, this displacement gives a higher starting torque. So this kind of motor, split phase capacitor start AC motor, has a very high starting torque. What it means is that you can start this motor under a given load, okay? And it will begin to take that load without burning out. At 80% of full speed, a centrifugal switch disconnects the start winding and capacitor. And again, here's where our centrifugal switch again comes into its own. But it has a capacitor in place with it as well. Okay. Capacitor can be 250 volts rated, as it is not always energized. Okay. But normally you'll find that they are 500 volts rated, basically for the additional safety of the capacitor, because your main supply voltage is normally 230 volts anyway. But because in this case here it's not it's not permanently connected in the circuit, they've recommended here 250 volts. But for normal work in real world time, you may find that 500 to 1000 volts rated capacitor might be more efficient. Let's just say that. Okay. And it would allow you to handle any surge in voltage, which sometimes happen in some cases. Okay. Now this motor cannot be speed controlled due to centrifugal switch. It runs at constant speed. Let's just make sure you can get this in play. Okay. It to reverse direction, swap star or run windings connections. Okay, similar as before. But each motor is different and has its own function. Again, do your own research. Okay. Let me just go back a little bit. Make sure that we got that in frame, in full. Okay. Okay. And here we have split phase permanent capacitor AC motor. Now, although all these motors may seem like they are the same, they have a different function, they have a different starting mechanism, they can handle different torques, etc. Their speed can, in some cases, be varied, in some cases cannot be varied. So get to know your motors. Same design as capacitor start motor, except there is no centrifugal switch. Okay. Capacitor must be 400 volts rated, as it is permanently connected. Okay. Now here you can have, you can see the difference in the voltage handling capacity. This will take into account any changes or variations in voltage. But normally, again, I would still recommend 500 to 1000 volts rated capacitor. Auxiliary start winding is also suitable rated for continuous operation. Okay. Motor has high start and running torque due to capacitor giving 90 degrees phase displacement and can be speed controlled. Okay. It runs at constant speed under moderately changing load conditions. To reverse direction, swap, start, or run winding connections. Okay, let's just make sure we get this orange. Okay, come on up. Split phase permanent capacitor AC motor. Okay. And here you have split phase motors are used in fans, pumps, and other load applications. Okay. And here you have, in all cases, the capacitor is mounted to the motor casing. It is outside of, it is attached to the main body of the motor itself. Okay, it is not internal. It is external to the working parts of the motor, as you will see as we go through this presentation process. Okay. Okay, we're good. I think yes, we're in full frame, so it's there for you to use. Don't worry about the vibration a bit, but I can't do anything about that at the moment. Okay. Now AC motor starters and speed control. DOL starters, direct online. Star Delta starter, auto transformer starter, soft start, variable frequency drive, rotor resistance starter, wound rotors. All motors over 0.37 kilowatts must be connected through a suitable starter system. And please note that these regulations, I believe it is still the same, but take into account any changes which regards may have happened since in respect of the 18th edition of the IEE regs. Okay, so bear that in mind. I am not sure whether this number is still the same. I have not checked it, so it will be down to you to check and make sure it is applicable. Again, safety, safety, safety. Sorry. Just make sure we got all that in place, okay? Yes, you have, okay. And this is our DOL starter, okay? Let me just get a closer look and look into it. Okay. All right. Can be single or three phase. Only to be used for motors below 5 kilowatts. Different coil voltages are available. Provides no volts coil, safety operation, hold on contact A. Okay. Has momentary action on start switch. Now, especially when I was at college, I had to draw this out and then write about how it works. So all this information here I had to write out myself by research and draw the diagram of its function. You guys have it easy these days. You come like you don't even do much work. Has adjustable motor overload coils. Sorry. Okay. Let's just make sure we get this in frame in full. Okay. Yes, you're in direct. Okay, thank you. Okay, good. Good, it's in frame. Okay. Now, when I normally run this system here, okay, it normally just to show you how it works, but it normally runs on my other computer, but it's not running too good on this. So this motor here normally works and runs, okay, but I have to admit that in this case it has not done so. But you can see the changes of colors as it mains off, okay, motor contactors, motor overload coils, three-phase motor. Now I'm not going to try and talk through this to you, so you will need to take the time out to look at it for yourselves and see it in operation as I click through each stage. Now here you have mains on, main supply. If you follow the circuit, you can see that you have your hold off coil, okay, is retained, okay, through this from your two phases, okay. Okay, main supply on, okay, and you now have your motor running, basically motor conductor of motor overload coils, okay, three-phase motor. Now this normally rotates, but for this, on this system here, this program does not make it run, so I'm just gonna have to live with that, okay. Now stop button pushed, you can see that stop button has been pushed, okay, circuit is now open, okay. Okay, stop button goes back into place, okay. Restart, okay, punch the restart button, okay. I've punched the restart button, okay. And yes, I would have liked to have seen it working, my motor's running, but it normally does, but on this occasion, it hasn't, okay. So I do apologize in that sense, okay. I may have to run it on a different computer. Okay. Now here we have motor overheating, could be the bearings, okay. And what's going to happen now when we have the motor overheating, okay. Motor overload coils activated. So you have your motor overload coils activated, overload contact open, okay. Pull those out into play. They trip drop the load off from the motor. Okay, let me just go back a little bit. Okay, motor overload coil activated, and here is where you now have your motor overload coils protecting your motor from harm. Once it operates, there's no further current can go there, it's causing any further damage. Okay, so you've saved your company money and you've saved yourself a lot of work. You simply then need to reset these or replace them depending on the types that they are, and then start to take it from there. Okay. Okay. DOL components. You don't need me to read this to you because you can read them for yourselves. Okay. That is our DOL contacts, relevant components. Okay. There's something quite satisfying about wiring up one of these starter DOL starters, and then you press the button and you know the machine works. Something quite satisfying about it. Or if you have a fault on it and it doesn't work, you then have to go and figure out why it hasn't worked. And often you find that the overload button has been reset too fine, so rather as you push the start button to start it, it trips out. But never mind, that was just in my time. Sorry about that. Okay, good. Delta starter. Used for AC motors above 5 kilowatts. Okay. Motor has 6 terminals to allow its windings to be connected to the starter as either star or delta. Motor is started in star, voltage current and torque are all reduced. Now it starts in star and it runs in delta. Okay. Interlock prevents motor trying to start in delta. Okay. When motor is up to speed, starter switches connections over to delta. Full voltage, current and torque are now present. Changeover can be manual or automatically timed. Electrical mechanical interlock prevents a simultaneous star and delta connections. Star delta starter. Okay. Compared to no man. Okay. Sorry about that, it's just my phone giving some noise. Okay, auto transformer starter. Okay. Okay. Use a multi-tapped transformer to control voltage and current torque as motor starts. Smooth control compared to 2-position star delta starter. Sorry about that. Only requires 3 connections to the motor. Interlocks prevent motor transformer tapping position. Okay. Contains same safety features as DOL. Never mind that. Okay. Let's make sure that we can get this up and okay. Soft start. Okay. And that's the soft start system using thyristors and triacs. Use these thyristors to control voltage and current torque as motor starts. Okay. A thyristor is an AC switch. By controlling the firing angle of the thyristor, AC voltage can be controlled. Okay. Programmable starters can be configured for different motor uses. Have the ability to precisely control acceleration and deceleration of induction motors. Have same safety features as other starters. Okay. Compared, never mind that, irrelevant. Okay, but you can see that now. Okay, and let me just go into that. Make sure you can get that on your screen. Okay, this is in full view. Okay. Variable frequency drive. That's what that is. Okay. Okay. Unlike a soft start switch, soft start which controls voltage, a VFD control frequency. So you have a frequency control device here. Okay. Synchronous speed is determined by frequency. Bear in mind that it's a 50 cycles, so if you reduce the 50 cycles per second, you will reduce the speed of the motor, vice versa. Main frequency is converted to DC. This charges reservoir capacitor and provides high voltage DC. This is converted to AC at variable frequencies determined by the drive and its program. Okay. Starters provide precise speed control and are fully programmable. Drives are selected based on motor size. Has same safety features as other starters. Let me just go over and make sure that we can get that into full view. Okay. Okay, thank you. Okay. Never mind that, that's not relevant anyway. Okay, thank you. Rotor resistance starter. Okay. Use wound rotor AC motors. These motors are required to start on a high load. External resistance are connected in series to the rotor windings. As motor starts up, the external resistance are reduced in value until they no longer add to the rotor resistance. This method provides high starting torque and current that can be gradually reduced as motor speeds up and is assisted by its own inertia. Has same features as other starters, etc. Okay. DC motors theory. Okay, this you can read for yourselves now. Okay, and here we have your DC armature. Okay. Okay. Now you can read this for yourself now. I don't need to be reading this to you up now. Okay, and you can carry on with that. I'll bring it in stage by stage. Okay. Okay. And you can read that for yourself now. Okay. And here you have series universal motors. Okay, again you need to draw these out. Can work on either AC or DC. Okay, all windings, field and armature are in series with each other. Okay, speed is dependent on load. The motor can be damaged if run with no load. Okay, to change rotation, swap connections to brushes or field windings. High start torque. Used for drills, vacuum cleaners, DC trains, etc. Highly efficient. Can be speed controlled. Okay. Shunt motors. Okay, and here we are. Okay. Field and armature windings are in parallel with each other. Speed is fairly constant under load or no load. Low start torque. To reverse rotation, swap brush or field connections. Used for constant speed application with varying loads. Can be speed controlled. Okay. And let me just get around that side to make sure I can get that all in on frame. Okay, let's get that in frame first. Okay. Yes. Shunt motor, okay, and it's in frame. Okay. Compound motors. Okay, again this you can read for yourselves. I won't need to read this out to you. You can sorry, let's just bring this up so we can get this into frame, okay. Okay, yes, you can, we can. Okay, yes, okay, yes. Let's make sure we can do that. Okay, alright. Okay, good. You can read this here for yourselves now. Okay. Won't need me to read this out now, basically. Okay, this is motor starting and speed control. Okay, and here's your In position N, the start contacts goes forward. Okay. And let me just move forward so you can see this for yourselves clearly. Okay. I won't read this out. You will read this for yourselves. I don't. Okay. And I'm going to leave it there for you to actually see for that time being. Okay. So let me just see if I can go down and bring this in left to right.